Okay, so I'm going to end with the beginning. And we're going to end by talking a bit about the processes that deals with reionization. And so, to remind ourselves, this is the thermal history of the universe. And now I'm reviewing what I talked about on the first day. We start at the time of matter radiation equality. As we've seen, that's a very important part of the universe, but there's nothing to do with, galaxies didn't exist then. That's redshift about 3000. When the universe was about 3 times that size, it recombined, and soon afterwards, baryons and photons decoupled. And that's when we see the surface of last scattering. That's right here. Redshift of about 1000. So at that point, the universe was about 2,800 to 3,000 degrees. About 3,000 degrees, right? Which is 2.73 today. Then, from here onwards, the universe was neutral, completely neutral. It was only consisting of, essentially only hydrogen and helium. There's a tiny bit of lithium around. And hydrogen and helium were completely neutral, and there was nothing that you could see. It was dark. There's no sources of light in that period. As I'll show a bit later, talk about a bit later, there are a couple of things you possibly could observe, at least at the later stages, but very little happening. Then we know that the universe today is ionized. We can see through the universe today. And that means that at some point between redshift of 100 and redshift of the first objects that we can see, the universe became ionized, reionized. And this is the process we're interested in, because that in many ways is the last frontier of galaxy evolution. That's the bit that we don't understand. So I'm going to start a little bit by talking about how we probe this. Okay, that's a very useful thing to know. And we probe this typically using what's called, or at least one of the starting points, is we use the Lyman alpha line. And we're going to start out by talking about the Lyman alpha forest. So here is a spectrum. It's the energy per wavelength of 2 quasars. These are both quasars. They're powerful sources of emission. They are different redshifts. This is at redshift 0.15, very nearby. And this is a distant quasar, one of the brightest in the sky, at redshift of 3.6. You can see, first of all, you can see that the spectrum is in the rest UV. No, it's in the ultraviolet. Okay, this is the actual wavelength that the light comes to you. So it's corrected for redshifting. And so what's the features that you want to see in this plot? The first thing you obviously see is that there is this feature here, this emission line here. That emission line is Lyman alpha from the quasar itself. Now, between the quasar and us, there might be gas. And that gas, because the most abundant element in the universe is hydrogen gas. And what happens when that light hits us? Well, first of all, hydrogen, the main transitions in hydrogen, in this case in the ultraviolet, is the Lyman series. Okay? So the first thing you can notice is that you will, if it's between us and the distant quasar, it will not show any lines blueward of Lyman alpha because of redshifting effects. It will always happen on this side. So this is the emission line from the quasar. This is an absorption line from gas between the quasar and us. Here's another one. And here's another few. Here's another one. And this is Lyman beta from the quasar, I think. But I'm not entirely sure. And on this side, you can sometimes see features as well. And these might or might not, in this case I don't think they do, belong to these absorption features. So that's the nearby quasar. There isn't a lot of gas between it and us. What about the distant one? Well, here you can see it looks very different. So there are no absorption features on the blue side, on the red side of Lyman alpha, because there is no hydrogen that's further away from us, and the quasar can't be in front of it, right? So all the absorption is on the blue side, and each absorption feature here is a cloud of gas. And this, you can then add this up and you can make it measure the amount of gas in the intergalactic medium between us and the quasar. You can use this as a way to map, because each absorption feature corresponds to one given redshift, and that then gives you a distance. So that you can actually map out where there is gas between us and the quasar. So let me illustrate that better with a movie. So, oops, I thought it wasn't going to start automatically. Let me get over here. I need to, whoops. Okay, so I'll explain. So this is a kind of a quasar. Yeah, guys, the idea here is that this represents the quasar. Yeah, and this blue stuff is supposed to be gas between us and the quasar. Here is the quasar spectrum. It's where you start. This is Lyman alpha. This is Lyman beta. And here is the Lyman limit, equivalent to the Balmer limit. This is at 912 angstrom. There are no lines in hydrogen beyond that. Here is another line that you can see in quasar spectra. It's a carbon-4 line. It's typically an emission in quasars. It's a very energetic line. And the same thing with silicon-4. So now what's going to happen here is we're going to follow the light that's emitted from the quasar. So this light, we're now going to follow that light as it travels through this gas. Now I'm going to run it a couple of times so you actually can follow it properly. But try to see what happens when it goes through this gas, what happens then in the spectrum here. Okay, we are over here, and we're looking towards that quasar. So my eye is here, looking towards the quasar. Okay, now let's play it once. And now it doesn't want to start. Okay, that's good. So now you can see what it does. It adding up, every time it intersects one of those clouds, you get an absorption feature.
Wow. Lensing.
Oh, that was a big one. Yeah, it doesn't take into account lensing, this one. It's simple.
Wow.
And eventually it's finished. Okay. Now, let me go back and just hold here. Okay. So the first thing, you see it comes through, you get something multiple places. Does anybody guess what this is? What's causing that?
Hydrogen.
It's all hydrogen, exactly. So this is hydrogen alpha. Close to that. This is hydrogen beta. This is hydrogen gamma, delta, epsilon, and then 6, 7, 8, etc. No idea where that went black. Probably because I must have touched something. Right. Okay, so that was one thing I wanted to get through with this, that there is multiple sets. So now also try to watch carefully and see what happens when it goes through the spiral galaxy. See what new ends up. And you see as you go up, these H beta, oh yeah, there comes the spiral. Okay, so what was the main things that happened? Yeah, there was a very strong absorption. And there was more absorption lines. So both of those were true. So the first thing, if I go from the blue end, is that you get this strong absorption here. And the other one is that you get these extra more absorption lines. This is because you get a lot of hydrogen and you saturate the line. Completely saturated. And it just blocks all the light. Here the flux is 0. And then if you remember your quantum mechanics or your line formation, a line, when it's strong enough, has these Lorentzian profiles in the edges. And that's what you're seeing here. So it becomes quite wide and very deep, and it blocks the light completely. That belongs then to these spirals, because you're going through the spiral, there's a lot of gas in here, and you block it. These lines here, that's metal. Those are absorption lines of metals in this quasar. This line here, this line here is carbon-4. Here's the carbon-4 emission line from the quasar. This is carbon-4 in this galaxy. So now you see, if you could get a spectrum like this, you can actually go and map and measure the amount of metals around these galaxies. So what people do sometimes is they try to do this at different distances, and then you can map out a radial abundance of metals around these galaxies. But that's the main things that happened in this video. So let me just go through, started from just run it one last time, and then hopefully you now seen these multiple, Lyman alpha, Lyman beta, Lyman gamma, and see as you go closer and closer, they start to overlap. And that makes it difficult to analyze, because you don't know what belongs to what. But now at this point, they're clearly separated. Lyman alpha, Lyman beta, Lyman gamma, but you can't observe it there because you need it to be at a much higher redshift. But you see, in practice, what happens here is that it eats away a lot of the flux here. Right? It really gets rid of lots. So that was a simulation. The real world, or you know, a funny movie, the real world, however, looks not dissimilar. So this is a very nice compilation that was done by Xiu Fang, and in an annual reviews article. And here are quasars at different redshifts. This is redshift 5.74 all the way up to redshift 6.4. This is all very distant quasars, but they are kind of routine today as a quasar. And what you see here is again Lyman alpha. And on the blue side of Lyman alpha, there's almost no flux. And that's because there's so much gas between this quasar and us, and this is not a very, very high resolution spectrum, that basically everything is gone. Almost everything is gone, but there is a little bit more here than there is here. Here there is a couple of gaps, but in general here it's essentially 0. Here it's a little bit above 0. So this is something that we would like to understand, because this is telling us something about the content of the universe between us and them. So to do that, it's useful to just calculate the absorption. I'm not going to go, I wasn't planning to go through this on the blackboard because I think this is quite standard stuff. But just to remind you, if you have a box of length delta L, and you have a flux F that goes in on one side, then if it's not hydrogen inside here, some of that gets absorbed. And the amount that gets absorbed is proportional to the flux, to the density of hydrogen, to the cross-section of absorption, and to the length that is gone through. It's just an optical depth definition. And that means that the actual absorption is going to be, the actual flux that you get out is going to be attenuated by e to the minus tau, where tau is the optical depth. So that's just how optical depth is used in all kind of calculations. And you have a situation where your optical depth is basically given by this integral over density over dl. Okay? That's optical depth through a simple slab of hydrogen. The cross section, sorry, sigma. Oh. The cross section we know from quantum mechanics, it's of this shape in general. In general, most of these absorption features that we saw in that video are very sharp. So that means the absorption is very slight. When the absorption is very weak, then the absorption cross-section is essentially a delta function. If it's a very strong absorption feature, so that if actually it's useful perhaps to see that in the movie, just to go back to it. Now it stops. I don't understand why. Let me just go to the spiral again. There we go. So here, you see the shape of these lines. They're essentially a delta function. It's just one point, right? Here, it isn't. It's a very strong absorption, and you can clearly see the line profile, which has a Lorentzian shape. Most of the times, I don't care about those lines. I'm caring about these Lyman alpha forest lines, these thin ones. These ones we actually call damped Lyman alpha absorbers. These ones I call forest lines. We're all interested in the forest lines. In that case, you can write this cross-section of hydrogen very simply as sigma h as a function of frequency is some central cross-section frequency and nu minus nu naught. That's the most common way of writing this expression. And the cross-section is quite small, of course, 10 to the minus 18 centimeters squared. But if you have a lot of hydrogen, say you have hydrogen of the order of 10 to the 17 or so, then you get significant absorption. Okay, so how do you actually calculate that in a proper setting? Well, we do it. I just take this expression here, and I say the extinction at some frequency, and some observed frequency, nu obs, is the integral, and that's where you can see here, it's the integral from nu observed to nu observed 1 plus z, which is just correcting for redshifts. That's integrating along the line of sight over all frequencies that you probe along the line of sight. So, and it's NH1 because you need neutral hydrogen. So you only care about neutral hydrogen of Z. You need the cross-section of hydrogen at a given frequency. And since everything is in frequencies, you would like to get to frequency. And yeah. And the original integration was about along the line of sight, dl. And here I am doing frequency. And I'm doing d nu dz, or dz d nu. That comes in here, dz d nu gives me nu obs here. That's what the final step in here is. And then you can use this delta function to do this integral. And you get, there it is, this cross section divided by its observed frequency, the H1 abundance at that redshift, and the line element at that redshift. So that's the absorption at that frequency. And it's just a change of variables in this integral. Now, that's, let me see if I want to move forward or not. Okay, well, we can do that, I guess. So, I haven't truly gone through all of general relativity with you, so the next step you might not be so familiar with. But the line element, dl, in general relativity, or in the kind of cosmology that we have, is given by c times dt. Okay? It's just a distance that light travels in some time. This is from the metric, so it's something we haven't talked about. And that you can write down. So that's dt. Which one did I go for? I went for dA first, yeah. dA and dA dz times dz. And the reason why I wanted to do it like that is I would like to connect this to the universe, to the expansion of the universe. So I would like to get A, the scale factor, into play. And the first thing here then is C, and this is 1 over A dot. Then A is 1 over 1 plus Z, so dA dz is minus 1 over Z squared. Yeah. So that's minus 1 over minus A squared. But there is an absolute value here, so I can get rid of my minus sign. And I get A squared times dz. And that is A over A dot is 1 over the Hubble parameter, Z, times A, but I would like to get it in redshift terms, so then it's 1 over 1 plus Z times dz. So that's what this term here is, dl dz. It's this expression here. So then we have a nice little expression here. We can put it in here, and we get it's useful to write that down. Then we get the extinction at the given frequency is, it depends on the cross section of hydrogen. That's the same, of course, at every redshift. You don't care about that. It depends on the Hubble parameter. That's the present day size of the universe. It's just a length scale. And this is a probe of cosmology. And then you're left with NH1 of Z. So now the question is, how do you deal with that term? Because that you also need to do. This has to do with the density of matter in the universe. So the easiest here is to rewrite it a bit. Let's write it first relative to total energy hydrogen density. So NH. Then NH, let's relate NH to the mean density. The idea here is you have a density, and what you should look to is to relate that density to the density of the universe. Okay, because we have the critical density, we know how to calculate that. So let's see if we can get that one in. So let's relate this now to the mean density. And then, so I've only rewritten it a bit. Now rewritten a bit in the sense of getting in some things that are physically relevant. So let me see if it was exactly what I did on the next slide. Yes, surprisingly, it was. And so what is this? There are three terms now. So instead of just doing this density of atomic hydrogen, I have three terms that have physical meaning. This term here is the neutral fraction. It's the fraction of the universe that's neutral. That's an interesting quantity because reionization, before reionization, this will be 1. After reionization, this should be very close to 0. So this, in a way, is what we want to find out. We want to find out what's the neutral fraction of the universe. And we want to trace it and see it changing from 1 to 0. And then we have found reionization. It's not going to work like that, but anyway, that's what we would like to do. This here is density relative to mean density. That's the overdensity, right? 1 plus delta is density divided by mean density. So this is overdensity. Density. And that's the mean density. So maybe it's useful to see what that mean density is. We know what the mean density of the universe is. It's omega something times the critical density. That's what we usually write. So let me write down what's the density of baryons. It's the easiest way to start. So the mean density of baryons, large B. I'll put a bar over just to say it's mean in this case. That is omega baryon times the critical density. That's the definition of omega baryon. Now, what's this? Well, if the universe was only hydrogen, you could just divide this one by the mass of hydrogen, and you would get the number density of hydrogen. Right? In principle, that's all you needed to do. In practice, let me see if I have it here, because it should be, yeah. In practice, we will write the density of hydrogen, mean density of hydrogen, as the mass fraction of hydrogen, that's X, so it usually is written as, times the rho baryon divided by the mass of hydrogen. That's the number of hydrogen-like things, and that's the mass fraction of hydrogen in this whole equation. Okay? So you put these things together, and you get that expression that is there. X over mp, omega baryon, critical density, it's 0 times 1 plus z cubed. So now we have that at least. So we have this an expression for this. This is related to the overdensity. So this is going to be something related to 1 plus delta. And this is the neutral fraction. Okay, so if you put that now into this equation, and now I'm stopping writing it on the blackboard because now it becomes quite long, you get this expression for the optical depth at a given frequency in hydrogen, in Lyman alpha in this case. Okay, so what's the things, the important things to note here? Well, first, let me just go back. Where does this tau come in? Well, it comes into how much light you've lost. E to the minus tau is what matters. So physically, tau itself is not important. It's e to the minus tau that matters, because that's the amount of light that's gone away. Now look at this value. Okay? This is the neutral fraction that varies between 0 and 1. So if it's 0, the optical depth is 0. If the neutral fraction is close to unity, this thing is typically large, right? Larger than 1. Then the typical optical depth for anything that has significant amount of neutral material, say 50% ionized, say this is 50%, then the optical depth is of the order of hundreds of thousands. So the effect on your light source is e to the minus 100,000. That's a small number, right? So it means that this if you're even close to, say, even if you're close to 10% here, you're still not going to see anything because it's extincted by e to the minus 100,000. You know, you don't have anything left of what you started with. So this is a very bad, and it gets worse because this goes up as 1 plus z. So where you're interested in working is at redshift 7 or 8, where reionization might happen. And then you have a cube here as well. So this thing will be huge, and there's nothing here that can help you if the neutral fraction is significant. So these probes that use hydrogen, and that's what the idea was to do here, was to measure the light on this end, and then that will tell you how much light has been removed, and that can tell you the neutral fraction. Let me show you that as well. So you can estimate that or set this to some number you think is right, and then you can solve your equation for this. That's what you try to do. And it doesn't work. It's not good enough to get reionization. So what we have used instead is we're using CMB results. And what you rely on there is the fact that as the light from the last scattering surface comes through space, when it encounters electrons on the way, it gets scattered off the electrons and gets slightly polarized. So you look for a signal of polarization in the cosmic microwave background. And if you do that, and actually the calculation is almost identical to what we had here. There's a difference here in that this is going to be the Compton scattering cross-section, but otherwise it's exactly the same calculation. You find that the reionization redshift is at some point after redshift 12. Yeah? Yeah. Yeah, so the neutral fraction should be 1 before reionization, and then something shall happen. Now we don't know how it happens. So there is if I plot the neutral fraction, H1 over NH, so the fraction of neutral, and I have redshift here, and I have redshift 500 here, and redshift 0 here, so it's the reverse axis. And here is 1, and basically it's 1, and then it's 1 minus 10 to the minus 6 or something like that. It's not completely neutral, but it's quite close to it. And then the question is, what happens? Okay. It could be that it basically goes like that. Okay, there's an abrupt reionization. It happened at essentially in one redshift, or it could be that it's not quite that abrupt. It could be that it went down like this. Then there isn't a redshift of reionization, but there is a period of reionization. Or it could be that it went change color again. Or it could go multiple times. It could go whoops, whoops, and then finally go down to 0. We actually do not know. We have no idea. Most people will probably guess that it's the relatively quick turning on. And most simulations also indicate that it is, but it could be more complex in principle, and we don't fully understand it. So this is indeed 1 before reionization, and then it becomes some small number. Today it's of the order of 10 to the minus 6-ish, something like that.
But the period, the time of reionization
Yeah, that's what it probably does. And this is exactly what, this is where the uncertainty comes here. Because if these stars form very early, then they could ionize a bit of the universe, but then the universe is so dense that it will recombine again and become neutral again. So if the stars live very short time, then die off, then the universe can become neutral again. If the stars start forming, and then more stars forming, and more and more and more and more, then it will actually happen very quickly. So it really is the period, not so much the lifetime of the stars, but how quickly they all form together. And so I'll show a simulation of it later, but that's indeed the question here is how that process of forming the first stars and the first galaxies work is going to determine how these functions look. And it's quite a big question for now. So you could look at this the other way around though, because this factor is so high, it means that it's sensitive to very low overdensities. Okay? So if this, you can probe very small numbers here, if you can detect anything, okay, because of this effect. So that's where this Lyman alpha forest comes into play. So this is what people then have tried to do. They tried to use this technique in this to go towards reionization. And so here is one of these examples. So you use this equation that I showed you earlier. You calculate this optical depth from the observations. So you know what the input spectrum is because you know the quasar, so you know what the flux is, and then you measure how much is left. Okay? So maybe I should draw it. So you have a model, and that says that your quasar spectrum looks a bit like this. Okay? That's its starting point. And then you go out. This is true. And then you go out and you observe it, and you observe something that's pretty similar, but it has some structure there. Okay? And then you say, okay, now I can see what happened here. I got, this is F obs here, and that's F in. So my F obs to F in, or maybe I should write it more other way around, is equal to the input times e to the minus tau at that frequency, nu obs. See? So now you can use this observed value and what your model says should be the true value, and you can get an estimate of the observed tau. So this gives me tau nu obs is minus ln f obs over f in. Okay? So that's how you go about calculating these values. And then you plot them up. So here is this tau value calculated from these quasar observations and many more that I showed you earlier as a function of redshift of the quasar. So this is probing the gas between us and the quasar, and what you can see is that this optical depth, this one, increases steadily as you go back in time. And the simple interpretation of that, now that I erased it, was very clever. The simple interpretation of that is that what's changing is this, that the quasars themselves are in very similar environments. So this overdensity should be about the same. But this changes systematically as you go back in time, and the universe is becoming more and more neutral as you go back to redshift of 6. So now we have two numbers. We have on one side, we have the cosmic microwave background. It says that the reionization happened after redshift 12. It's up here. And this one says that the universe is still pretty pretty transparent at redshift 6. This is a better view of it. And then there are some other lines here, and those are attempts at using the other lines I told you about, Lyman beta, Lyman gamma, etc. It's possible to do that, but it's challenging. Here is converting it now into the neutral fraction. So the fraction of H1. And now you can see the numbers. This is no longer the optical depth, but it's actually the neutral fraction. And these are various observations and some weighted average of these. And you see this is 10 to the minus 3, 10 to the minus 4. So even at redshift 6, what they're saying is that only about 1 hydrogen atom in 10,000 is neutral. Right? That's not very neutral. The neutral fraction of 50% is what you would call, okay, now we've gotten reionization. So this is still the end of reionization. You're far away from 1. 1 is very far up here. It's a logarithmic scale. So even the most extreme points here are, you know, several, 1 atom per several thousand is neutral, and you want to get 1 in 2. So it's nice, but it's not quite there. So you would like to get a little bit more understanding of these quantities. And for doing that, it's useful to think about the universe as if it was in thermodynamic equilibrium, or photoionization equilibrium, sorry. In equilibrium, the number of ionizations per second should equal the number of recombinations per second. That's the equilibrium solution. Then you recombine and ionize in balance. The time scale for recombinations you can write down. It's known for hydrogen relatively well. It's given in this form. The time in recombination depends on the electron density, because that's what needs to hit the protons, and the recombination coefficient, which is given in this form. This is a fit to it isn't truly a power law like this, but it is a fit to the recombination coefficient from quantum calculations that work over the kind of range of temperature that we are interested in. So quantitatively, if you put that in, if you put this into here, you can then calculate what the typical recombination timescale is. Assuming this. No, not assuming that. This is just the recombination timescale. And this comes in from estimating the electron density. That's when this comes in and where this comes in. Okay, it's the same calculation I did earlier to do this, but now doing it for the electron density. I'm not going to do it again. Okay, so that recombination time scale in kind of typical conditions in the universe is about 5 billion years. It depends on redshift to the minus 3, so it's much shorter at high redshift. But remember that the Hubble time scale of the universe is about 10 to the 10 years today. Okay? So this is actually quite close to the Hubble expansion time. And so what that means is that if you're in the low density region of the universe, it's actually difficult for hydrogen or proton and electrons to find each other, because the universe expands on a time scale that's comparable to the time scale they need to recombine. So it's actually difficult to make the low density universe neutral now. It's easier at high redshift. So as you go up in redshift, this thing will drop dramatically. So if this one goes to 100, right, then this is about 1 million, and your recombination time scale is about 10 to the 3. So at higher redshift, it becomes easier because the universe was denser. And the more diffuse the universe is, the harder it is to make it neutral again. Now, if you do the photoionization equilibrium, it basically says that the number of neutral hydrogen divided by the ionization timescale should be equal to the number of ionized hydrogen divided by the recombination timescale. Because this is the timescale it takes to go from ionized to neutral, and this is the time scale it takes to go from neutral to ionized, and that should balance. Those two should balance. And you can put this in, you actually have some estimate. So the recombination timescale is an atomic feature. The ionization timescale is not. The rate of ionizing photons depends on the sources in the universe. So we often put that in as a free parameter that you then go and you use observations to constrain this parameter. And it's found to be of the order of 10 to the minus 12 per second. So you can then put in numbers the recombination timescale, which I had on the previous slot, and this rate, gamma, for the ionization parameter, and you get an estimate of the neutral fraction in photoionization equilibrium. Okay? So this is when the universe has ionizing sources on this side, and it basically, this tells you how neutral should the universe be with that set of ionizing sources. And it tells you that at redshift 3 or so, it should be very ionized, 10 to the minus 6. There is enough ionizing sources to keep the universe very ionized indeed. But you also see that if this changes significantly, or particularly if it gets very small, or if redshift goes up a lot, so this means either there are less sources or the universe is denser, then this neutral fraction is going to go up quite a lot. So again, this is a view into reionization. And so here is what it looks like at redshift 3 in terms of quantities. You put in sort of typical observed quantities. We find that the intergalactic medium at redshift 3 is about 20,000 Kelvin. And you can determine that from these Lyman alpha absorption, because they will have a slight width, and that width is set by thermal motions. And you find that the recombination timescale is about, in this particular case, about 9, oops, is that right? I'm actually not sure that number is right. I don't think it should be 9. I thought it was 8, but okay. It's, I'm not going to check it right now, but it isn't, the correct value is in the summary notes. I think this is a typo. This looks too long to me. Because at redshift, yeah, I'm pretty sure that's too long. But the relative point, anyway, is fine. The recombination timescale is quite long compared to the photoionization timescale. And so this is a physically interesting thing. It means that when you turn on a source, okay, say I could turn on and off stars with turning a button or a handle. I turn on that star and I turn it off again. Okay? It's almost instantaneous that I ionize the gas, but the gas will take quite a long time to go neutral again. So I turn it on, turn it off, eventually it goes down. Here in this case, it's 4 and 5, if this is correct, 4 or 5 orders of magnitude difference. So it is very quick to ionize and very slow to recombine. That is only true at the densities that we are considering. Okay? And those are not densities that are relevant for life on Earth. Right? We're talking about densities of 10 to the minus 20, many, minus 28, minus 27. Those are densities that we can't even make on Earth. If your density goes up a lot, if you're much denser, then your recombination timescale will go down very quickly because it depends on density squared. Okay. So you can fill in of this into this expression for the optical depth, and you get this expression, which depends now on the photoionization background, the temperature of the gas, the redshift, and the overdensity. And this is often how you see this particular expression written. That's the expectation for a universe that's in photoionization equilibrium. Okay, So before we continue towards the final bits of reionization, it's also useful to understand a bit better the thermal state of the universe. And this is a what we call equation of state diagram or state diagram of the universe. Here on the x-axis is the density, or the overdensity rather. So the gas density divided by the mean density. So this is delta, logarithmic. On the y-axis, you have the temperature, logarithmic. So now there are at least 3 features in this diagram that are interesting and we would like to understand. And this is how the universe looks quite soon after reionization. The first is this line. Why is there a steady trend here? Second one is this trend here, which also is a bit peculiar, looks very tight. And finally is this plume of objects here. Now let's go through this, and I'll do it on the slides. But now this, what I've done here is I've written down the change in energy given heating, cooling sources, and PDV work. So that's just thermodynamics. When you write that down, you fill in what the energy is, kT, and you fill in these other terms for PDV work, you'll find that this is the equation that it satisfies. It's not so crucial to go through the full derivation here. I'm more interested in the physics that comes in. And it says that the temperature changes in response to 3 different ingredients. It changes depending on the particle number. That mu depends on how many, what is the mass per particle. Okay? So that mu will change if you ionize the gas or you recombine the gas. So the temperature changes because if you have the same amount of energy and you distribute it over 1 particle or 2 particles, that will actually make a difference in what your temperature is. So that's a small effect usually. It depends on heating sources, and it depends on the cooling sources. Relative to the internal energy is what is, that's just a normalization effect. And finally, it depends on the adiabatic expansion of the universe. So if you really want to see the full derivation, it's in the lecture notes that are on the web page, but I'm not going to go through all of it because I didn't expect to have the time to do it, and it takes a little while. Okay, so that's the balance of heating and cooling, as I said, and this is the expansion of the universe. At high redshift, which is what this previous figure is, this is at high redshift. I actually lost which redshift it is, but this will be at redshift 3 or so. At high redshift, the main cooling effect at low density, and what we were interested in now was the low density end, is inverse Compton cooling. Okay? Remember, that's the one that depends on density to the first order and 1 plus z to the 4th power. So that's the cooling effect that matters in here. And then it's a little bit of a subtle argument that needs to be made, and it's a little bit tricky to do without having done all the derivations in here. But if you require that all of these terms are independent of density when you are hitting thermodynamical equilibrium, then you find a thermodynamical equilibrium solution which basically says the temperature should depend on the density to 0.57 power. And that is very close to the slope of that line. So this part is in thermodynamical equilibrium where the main cooling is inverse Compton cooling. Very inefficient cooling, but it's sufficient to set up this equilibrium solution. What about the other terms? Oh, sorry, I didn't. What about the other bits here? Well, this part is shock-heated gas. So why doesn't this just come down here? Why is there so much up here? Do you have any idea? So it's mostly because of the cooling function. All right? Remember the cooling function from yesterday. It is at these kind of temperatures, and this will be very little metals in this gas. So at 100,000 to a million Kelvin, the cooling time is very long. So this gas will be shock heated, and it will remain there. It will basically not cool down, at least for a long time. So that's this gas, it's shock heated gas, and which just remains like that. This part is just because you get denser and denser gas, it cools. It cools better. The denser the gas is, the more it cools. And this part is put in by hand and doesn't really matter. It's again, it's density, but now it's virial. It's just that they are in, as you move this way, you get into bigger and bigger halos, and you get the halo temperature is higher and higher. And then this is essentially what this trend here is. Okay, so here is an evolution of this. And I need to explain what these two terms are. Okay. So what you're going to see here is that diagram, but now a movie. Here is a density. Here's the temperature. It's the same panel I showed earlier. Here is just simply where things are. It's the mass. Here it's weighted by the amount of metals. So this is also going to tell us where most of the metals in the universe are. At this point you don't see anything because there are no metals. Pretty much nothing. It starts at, the universe when it starts at zero metallicity to a good approximation. So it says that most of the matter is in a trend similar to what we saw earlier. Now as time goes on in the simulation, you can see that one establishes this equilibrium solution. There's almost no mass on this end, and almost all the metals are here. So now you can see the dichotomy between where the mass is and where the metals are. The metals are here and in a cloud here, and most of the matter is here. And the reason for that is very simple, sort of. On this end, you get metals from stars. You need to have a high density before you can get stars. And the virial density, well, it needs to be, more than 200 times the background density. Here they actually plotted in density, so it's hard to convert. So this stuff, when you start seeing it coming up, if I go back, it's about here. So it's about redshift 3. You see there is quite a lot of metals, and it all resides in bound structures, and a little bit is now being pushed out of the galaxies. This is shock-heated gas. It's typically gas that's been blown out through supernova explosions. The peak of star formation in this simulation is somewhere redshift of 2. We haven't reached it yet. But as it goes on, whoops, actually, let me do something before I suddenly have a problem. I'd forgotten to plug this in. Lucky we didn't die while I was in the middle of talking. Stupid, stupid, stupid. Okay. So now if I move this, and now you can see here, you can see very clearly, most of the simulation is here, which is where there are no metals. And that's because most of the material hasn't made it into galaxies and made stars yet. In fact, it stays around for a long time. So if I now move slowly forwards, you see now how that shock-heated part, which is winds, becomes more and more populated. And here, now you're hitting the peak of star formation, and it takes, of course, some time And eventually, you just continue to fuel this part of explosions and shock-heated gas. Some of this gas now is gas that's falling into big halos. These big halos, the 10 to the 14 solar masses, 10 to the 15 solar masses, have very high virial temperatures, and you'll start getting those halos here. At earlier redshift, you don't have them. So it's a mixture of two sources here. So this particular movie is from something called the overwhelmingly large simulation. So since they've used the word overwhelmingly large, then the next simulation they made they called Eagle, because.
So, how the average metallicity of metal particles or something they are mounting there?
So they are SPH particles, and so they get the tracer of metallicity per particle, and that's. But I'm not sure how they averaged it to get it here. I think they just.
Those are not stars.
They're not stars. They're biggish particles of the order of 10 to the 7 solar masses or something like that, and you just 10 to the 7, 10 to the 6, 10 to the 7. I don't remember the resolution.
Okay.
So they're quite big. They're a big chunk of a galaxy.
Okay.
So it's sort of an average metallicity for the whole galaxy.
So it's something like a nebula or...
Yeah, it's a big nebula. So it's not a very good measure of that, but it's sort of an average bit of a chunk of a galaxy. Okay, so now we're really going to get into the bit of keeping the universe ionized. And for that, we really need to create Strömgren spheres. So have you had about Strömgren spheres in your astronomy courses yet? No? No. So those are very nice concepts. Sometimes we see them in nature. But basically, the idea is in a Strömgren sphere is you start with a neutral sphere, hydrogen, and then you turn on a star or source of ultraviolet radiation inside here. Okay? That's going to radiate UV, and that UV is going to ionize some of that hydrogen. So now this is now H1, and this is now H2 or H+. Okay? So the idea is that if you have only hydrogen and you get one photon that ionizes, that's energy to ionize hydrogen, you just count up the number of hydrogen atoms you have. You set that equal to the number of ionizing photon you produce, and that's going to tell you that you can ionize all the hydrogen out to some radius because the radiation is isotropic from the star, right? So a Strömgren sphere is the region, is the sphere where a single star can ionize all the hydrogen. And the way you calculate it is you balance recombinations with a number of ionizing photons. So I can if I rewrite this equation, it might be a bit clearer. So I write the number, the rate of ionizing photons. So that's the number of photons with energy above 13.6 electron volts. So it's strong enough to ionize hydrogen. That is equal to 4.3 Rs cubed. That's the volume of that sphere times the number density, which I've written down here in terms of total number density. Sorry. Let me just think a little bit more to say it right. Right. Okay. It's not a good way to do it. Sorry. So that's the total number. But I want to have the number density. I want to have the rate of ionizing photons. And so let me go back again. So that's going to be what I want to do is I want to do number of ionizations should equal the number of recombinations. Okay, that's the equilibriums that we're looking for. Okay, so now we try to do the number of ionizations first. So I want that per volume element. So I do the number of ionizing photons from the star in the center divided by the volume. Okay. That's the number of ionizing photons per volume element. That should be equal to the number of recombinations, which I said earlier was given as Ne and NeH plus. What if the gas is only hydrogen, now assuming that here, ignoring helium, it's a small correction. If it's only hydrogen, then we can just say every electron comes from hydrogen. If it's fully ionized, this is equal to the number density squared. Okay, it's number density. Both of them are number densities. And that's the idea. So then you have, basically you have, if I have 50 atoms of helium, no, sorry, if I have 50 atoms of hydrogen and I have 50 ionizing photons, then I can keep that system ionized. I can keep that region ionized. If I have a sphere here and what I'm releasing is something like 10 to the 50 photons, so out of here comes, say, 10 to the 50 photons per second, something like that. Then that gives me the volume which I can ionize. And the solution is given in this form. And so any massive star will typically create an ionized region around it that looks a bit like that. So let me actually show you that, because I think I have one here. Whoops. This one back here. Okay. So here are some examples. These are single star H2 regions in the Large Magellanic Cloud. There's an ionizing star in the center, and the color here shows where there is ionized gas. So you can see they're almost spherical because there is a single star and it radiates out, so it should be spherical. And you can measure the radius. It goes up very quickly, and that's because it's either ionized or it's neutral. So here you can actually see these Strömgren spheres, and many H2 regions don't look like that because there are multiple stars and they have complicated geometry. But this, you can measure that radius, and in principle, if you can measure that radius and you can measure the density, there are some ways of doing that, then you can measure how many ionizing photons that star gives off. So this works. This works quite well. We know how to do this. It's a standard calculation. So what we want to do, though, is to do this, but now let the universe expand. This was for a static universe. And for an expanding universe, it looks slightly different. the change in the number of electrons at a given position depends on the flux of ionizing photons at that position and on the recombination. It's the same equation I have here, except I no longer set an equilibrium solution. So the equilibrium I had here, number of ionizations equal to recombinations, I didn't put that in here, otherwise it's exactly the same thing. So you can now try to integrate this equation, and what you have to do is you have to calculate some volume averages. To integrate these things and you average over volume, so you basically multiply all these terms with dV, and then you integrate over all space. And that's why I kept it in this form with the divergence here, because then it's easy to calculate. And then what you get is you get a number of averages. You get the average densities. Average density, this one integrates out nicely because it's a divergence. And you get one term, which is an average of these two densities. So it's this thing here called the clumping factor. And the reason why it's there is that if you have recombinations, if I put the same amount of gas and I spread it all over evenly in a box, okay, imagine that, it's not clumped, then I get a recombination factor. Now I can get exactly the same mean density, but now I put it all into clumps, okay? So I have a situation where my box is completely filled. So my density, average density, is what? 10 to the minus 5, 3 to the minus 3. Now I can do exactly the same thing, but now I put all the mass into two clumps. Okay? The average density, N, is still going to be 10 to the minus 5. But most of the volume is empty. Now, will the recombination time be the same in those two cases? It won't be, because the recombination time depends on density squared, where there is particles. Depends on the density where there is electrons and protons. And they are much closer to each other here than they are here. So here, you would recombine very quickly, and here, you would do very slowly. And that's measured by this thing we call the clumping factor. And what it relies on is that the integral of NE NP is not equal to the integral of NE times the integral of NP. Mathematically, that is not, you cannot factorize an integral. Okay. So that's this clumping factor. And this clumping factor then decides how efficient recombinations are to make your universe neutral again. When you put this in, you now have an expression for the size of these Strömgren spheres, these spheres I just talked about, as a function of time. And you can see they change with time, so there's no equilibrium solution here. It depends on the recombination time, it depends on how quickly the universe expands. And there are a couple of cases where we consider. One is a situation where the recombination time is very long. So the only thing you care about is you ionize something and then it stays ionized. Okay? In that case, this volume just goes steadily up. And it's basically you don't care about recombination. You just turn on a source and it just emits ionizing photons, And as long as it's emitting ionizing photons, the amount of region of the universe that's becoming ionized grows linearly. And you can see why this is important for reionization now. Because in reionization, what you get is you turn on the first stars or the first galaxies. They emit radiation, and that radiation needs to travel out and ionize the universe. And this is what we expect to do in the beginning, because the recombinations, as we saw earlier, are generally inefficient. So they take longer. So to start with, you ionize very efficiently, and the challenge is to keep it ionized. It's not so difficult to ionize it. But later on, the recombination time becomes important, and you want to keep the universe ionized. And in order to keep it ionized, you need a rate of ionizing photons that depends on the density of hydrogen and on the recombination time and on this clumping factor. So you can ionize the source very quickly. But now you have these electrons and protons, and they all want to combine to make hydrogen. So how do you keep it from that? Well, you emit more UV radiation. You just have to emit UV radiation to keep them from combining. And when you convert this into physical observable quantities, you conclude that you need a star formation rate, a rate of new stars, because it's these massive stars that ionize the universe. You need a rate of star formation that's about 0.002 solar masses per year per megaparsec cubed, with some dependencies on the clumping factor, on the redshift, and how many ionizing photons escape into the intergalactic medium. So let's see a simulation of this process. I've never found a very good one. This is the best one. It's really ancient, as you might see from the geometry. This is a volume of the universe. Maybe I should explain properly before it gets to the really fancy part. Okay. Okay, so this is a box, a simulation box of the universe. It's full of hydrogen. And now what's going to happen as this thing goes on is it's going to turn on, stars are going to turn on inside this box. And as you will see, in the beginning, the universe is really dense. So you will see these stars turning on, and they will ionize a little bit, and then that will recombine again and become neutral. And they're not able to reionize the universe. But as time goes on, you will see that that fact changes. There you have one source. Okay, it's trying to ionize the universe, but it's not really succeeding. Yeah, it's a futile existence. But then, as more and more of them come, and they start to overlap, their ionized regions start to overlap and start to fill the universe. And that's the idea. You create all these Strömgren spheres, and as they overlap, they fill more and more of the volume. And now you can see they excavated, significant regions around them, but they still haven't ionized the universe, but they're starting to improve. And each of these have these Strömgren spheres around them. And you see they blink on and off because there are sources that just last a particular amount of time. And eventually, almost all the neutral material, all this dark stuff, is going to be eaten away. Like somebody eating a cheese from inside. And finally, the universe is reionized.
There is fully ionized.
At this point, it's ionized to 10 to the minus 4 or 10 to the minus 5. So I don't know exactly where it's an ancient simulation. You see the Tron-like graphics, and there's no redshift indication or anything.
Again, these particles are stars or galaxies?
These are galaxies in this case.
Okay.
Well, they're treated as just ionizing sources, but they're assumed to be galaxies in this case. Maybe not at the very beginning, but certainly later on, they're galaxies. So this is crucially how we think reionization proceeds. There's another illustration of it that often is shown, which is this one. You're starting in this neutral phase. You get the first stars, and they create this small bubble of ionized gas around them. That was what we saw in the previous movie. But they can't ionize the universe because there isn't enough of them. And the density of the universe is too high. So they recombine too quickly. But then you come into this phase where all these bubbles start to overlap. So you have all these sources, and each of them, so each of these sources, they have their little bubble, ionized bubble. At this point, you're not reionizing the universe. Then as time goes on, their ionized bubbles become bigger. And now they're overlapping, and you can actually ionize the full universe. And eventually, and this phase here is the messy phase of reionization, is the phase when it goes to become completely neutral. But at the moment, the challenge, or what we really want to understand, is how to keep it ionized. How it's ionized is interesting, but it's not really observable at the moment. What we would like to know is how it's kept ionized. And the answer to that lies in studying very distant galaxies. So typically what you do when you study distant galaxies is you make use of one fact. The fact I showed you earlier. Actually, it's better to show you the real spectrum, I think. So let me go back very quickly. There we go.
There is a supernova.
Yeah, this one is not a supernova, but it could be. So what we utilize is this. There's no flux on this side, and there is flux on that side. So if I put a filter here, and a filter here, and a filter here, I would see this object in this filter, but not in this filter. And I can use that to estimate what the redshift is. I can compare it with a model like this, and I can say, okay, the redshift is about here, because if it was lower, I would see some flux in this filter. If it's higher, I wouldn't see any flux in this filter. And this is called a dropout technique, and that's how we find very distant galaxies typically. And here's a real example of this. This is one galaxy, and these are 4 different bands. And you don't see it in the Z band, but you see it in the Y, J, and H band. And this is going redder and redder as you go that way. And then you can conclude that this galaxy must be at redshift about 7. Because you know where that drop-off is. It's about 7,000, is at about 7,000, at about 1,000 angstroms, a bit lower. And so at redshift 7, it will be, the cut will be at about 8,000 angstrom or so, and it will be very little light in this band. And when you do that, you can then start to count the number of galaxies as a function of UV luminosity, but as I talked about yesterday, UV luminosity is the same as star formation rate. So you can count the number of galaxies at redshift 7, at redshift 8, and you can try to account for how many stars are being formed in these galaxies. And when you do that, you want to compare it to this constraint from theory. And here you see, as you go down in magnitude, and these are faint galaxies, okay? 29th magnitude is very faint. If the observations are in this gray region, then the galaxies that we observe at redshift 7 are sufficient to keep the universe ionized. If it's in this white region, what we see is not sufficient and something else must be there. And the observational data is in the at the time when this review was written, it's in this dark blue range. It's a bit tighter now. But you see it's consistent with both solutions. So we think the current situation is that we think galaxies are sufficient, but just to keep the universe ionized at redshift 7. There are lots of different comparisons here of different luminosity functions and see whether it works. And this says how faint we need to go in order to explain keeping the universe ionized. And in some cases, it's easy. In some other people's work, it's kind of hard. And in some people's work, it's almost impossible. And this is a challenge, and it really is at the limit of what we can do observationally today. So this is a comparison of the amount of electrons that you can infer are there from the cosmic microwave background, that's the gray region here, to the number of electrons that the galaxies should produce. And you see that we're not expecting to fit that until we get out to redshift of 15 or so. There's a bit of a tension. But we cannot observe these galaxies yet. Our observational limit is about here. So we're still not in a situation where we can test whether this works or not. There's a bunch of other plots here. And this then is what this group's best guess at the reionization history of the universe is. This region here is constrained by cosmic microwave background observation. This is the fraction of the universe that's neutral. Okay? So when it's 1 here, the universe is completely neutral. When it's 0, it doesn't go to 0 because it changes to a logarithmic scale here. So 0 is infinitely far down here. But what you can see is that their predictions is that the universe slowly, relatively slowly, over a range between 10 and 6 or 7, went from being completely neutral down to being something like 40% neutral. And he argues that this is not quite what you would see in these quasars, but that is because he thinks that the quasars look out through very special windows. And so let me go back to the movie, because that one shows that very clearly. If I go here, see here, imagine this was one of those quasars. It doesn't have a lot of stuff in front of it. So you can see this one really well. And you would infer, when you look at this quasar, that the universe is ionized. But actually, a large part of the universe wasn't ionized. It just happened to be ionized in the direction that you were looking. And so that is where there is a tension between using these quasars and arguing about the volume of the universe that's been ionized. So in a way, I'm going to leave it here. What I'm going to just conclude with is this statement here, that in order to keep the universe need you can ionize it relatively easily, but you need to keep it ionized. So you start ionizing something that's easy, that's quick, but then you need to keep it ionized and fight against recombinations. And this is an expression of how you fight against recombinations. And it gives a minimum rate of star formation that the universe needs to have. If it had dropped below that, the universe would start becoming neutral again. Maybe that has happened in the past. We don't know. Maybe this has happened in the past. If that's how it is, then galaxies today, if you go down to the very faintest magnitude of galaxies today, which is 29th magnitude, they seem to be more or less enough to keep the universe ionized. And so there's galaxies that keeping the universe transparent, and we don't need contribution from other sources like early black holes, AGNs, etc.
LT will go like few more steps at the right level with LT.
So JWST will, or the ELT can, yeah. So those two, so this here, I think will be resolved by the James Webb Space Telescope. It will clean up this part of the world. Some of it will be cleaned up by the ELT, but not very much. The funny thing was that I thought I had a plot in here which showed something else, but I seem to have lost it. No, I completely lost it. There is one other thing, and that is which I was hoping I was going to cover, but maybe I have accidentally hidden that slide. Aha, that's what I have done. Sorry. So I hid away one slide, which I also wanted to mention. I'm not going to go through the theory of this at all, but I was saying it is possible to go back into the neutral world, into the pre-reionization world. And how you do that? Well, the trick there is to go back and observe radiation, 21 centimeter radiation. 21 centimeter radiation is a hyperfine transition in hydrogen. It's a spin flip transition of an electron that goes around, and it's the flip between whether it has the same spin direction as the nucleus or not. And that's a very, very low energy transition, and it's not optically thick. So you can use it to peer into the universe at very high redshifts using radio telescopes. And in principle, this is from a simulation by Ilyev. In principle, you can use this technique to measure temperature variations, this is in millikelvin, of the gas into the neutral universe. So you can map out as a function of position in x direction and redshift, you can map out where there are hot regions. And these are the regions where the first stars form. It's well beyond the capabilities of current facilities, but we hope to see some signal like this in the near future. But in the longer future, with the square kilometer array, we should be able to map out these hot spots where the very first objects formed in the universe using this hydrogen 21 centimeter transition. So that's the future in many ways. This is something that is a key reason for building the 1 square kilometer array. It's one of the very few ways you could imagine going back and peering into the neutral part of the universe, the dark ages. It's really the unexplored frontier of high redshift universe, and the only way you can do it now is probably going to be in the radio. But it's not going to happen for another 15, 20 years, I think. We'll see. Okay. But that's it. I'm going to finish there. And if you have any more questions about galaxies and galaxy formation, then now is a good time to ask. Thanks. Well, for those of you that have looked at the problem set, or those of you who haven't looked at the problem set, it might be an idea to do that too, because that's, you know, I don't know how easy it is going to be. So it's, I think, building on, but there's actually one thing I didn't mention. I only mentioned to a couple of people. Let me just mention that on the web page, there is something called a cheat sheet. And I wanted to just show it to you. So I give this one out on exams. And what it is basically a collection of parameters. So if there is something that you feel I haven't specified or haven't made clear, then I don't think there are any, but there might be. Then the constants are all gathered in this page. Okay, this is what I don't expect anybody to remember when they do their exam. So it has physical constants, cosmological parameters. It has basic equations from cosmology. It also has basic equations from the growth of structure. And some bits and pieces about, the energetics of gas and this stuff I just talked about, as well as the virial relations, virial radii, virial masses, virial temperatures, the press Schechter, etc. So this one you can make use of. It's like, they might help you in terms of remembering simple and basic equations. But otherwise, it's just try to sit down and analyze the questions. And if you have questions about them, just let me know. But as I said, next week I am on holidays, so chances of me replying is not going to be 1. Okay. So no other questions, then I'm going to...
So Jarle, I just want to thank you for sharing this time with us.
It's been a pleasure.
You have a little time problems to come here. That, of course, you finally
we managed.
come here and stay with us during this week. So I just want to thank you. Of course, the students really like this kind of courses and this kind of teaching and learning. So thank you very much. I hope you can come back sometime.
We'll see. I wouldn't mind.
In the near future.
So,
before the big rip.
Yeah, that's right. Yeah.
So thank you very much again, and we'll see what will happen from now.
We will see. Yeah, thanks. And thanks to the students for showing up, actually, when you're in the middle of your finals. It's not easy. I can understand that. And it's not going to be so easy to do your problem set either.
Okay, thank you.
All right.